Hi, welcome to my talk. I'm going to speak about a hierarchical grouping algorithm for multi-vehicle dial-a-ride problem. This is joint work with Kelly, Alexandre, and Xiang Yu, and I am Shamantak, your speaker for the day. Uh, so our work concerns ride sharing, and as you all know, most of the app-based taxi platforms, for instance, UberX, it allows you to share your ride with other passengers. This is not only easier on our pockets, but it's also eco-friendly because of multiple passengers sharing a particular taxi. On the other hand, it's also important for the companies to make sure that customer satisfaction is not affected too much because clearly sharing your ride affects your travel time. So one has to come up with good algorithms running in the background of these apps, which makes the taxi allocations efficient. Now, the taxi sharing problem can be very well abstracted by a problem which has been known for a while now as a multi-vehicle dial-a-ride problem. So here is an abstract definition for this problem. So suppose I'm given a bunch of requests, each one of which has a source location and a destination, and a fleet of taxis which have an original starting location. The job of an algorithm would be to group these people into different clusters and then assign a taxi to serve each of these clusters. Now, one has to remember that the taxis have limited capacity, so it cannot be carrying more than a fixed number of passengers at a specific point in time. For example, if I look at the group of people on the extreme left, top left corner, then this taxi, it might first move to the first group of people, these two people, then pick both of them up, drop one of them, and then move on to the destination of the second person, drop him off, and pick the third passenger up. Then on the way, the taxi might pick up the fourth passenger, drop her off at her location, her destination location, and then finally it drops off the fourth passenger. Okay. Here, of course, I have assumed that the capacity of a taxi is two, but a similar example can be just made for different other capacities as well. Okay. So the question now is there clearly are various ways of grouping the bunch of passengers and assigning taxes to them. So which one do we choose? Which one is a good allocation, right? So in this paper, we design algorithms to minimize the total travel distance, which is a classical objective function that has been looked at for this kind of problems. There are other objectives that one might consider, and there is work done on them as well. But in this paper, we are primarily concerned with this objective. Okay, a bit of literature. So this problem turns out to be NP hard even in very, very simple case because it indeed captures the classical traveling salesman problem as a special case. On the positive side, there has been good polynomial time approximation algorithms known for this problem. But in the case when we just have one taxi to serve everybody. So Chalikar et al. Gave an order square root lambda times log n approximation for this problem, where lambda is the capacity of the vehicle and n is the number of riders. There has been a follow-up work by Gupta et al. Much later in 2010, who gives a slightly worse guarantee. But the importance of this paper lies in the fact that it showed connections of this dial-a-ride problem to several other interesting and classical problems in the area of network design and routing. However, the question remains, what about a polynomial time approximation algorithm for the multiple vehicle case? This is not known so far. So this brings us to our contribution in this work. So we design an algorithm which matches the approximation factor of the single vehicle case and also runs in polynomial time. To very briefly summarize, our algorithm is arguably much simpler than the heuristics that have been designed for the single vehicle case because it avoids complicated subroutines and sticks to classical things like minimum cost perfect matching, minimum spanning tree computations, and so on and so forth. So indeed, we did an implementation of our algorithm and we compared ourselves with two baselines. as we will see in the experimental section of this talk. So at a high level, our algorithm has a couple of phases. The first phase is what we call a grouping phase, which puts together people who have to be sort of assigned a single taxi. And the second phase is to decide which group is to be served by which taxi and what would be the route that the taxi is going to take. Okay, in particular, who is the taxi going to pick up first and drop off, and then who is the taxi going to pick up next and drop off, and so on and so forth. Okay, so both these phases are non-trivial, and we design algorithms and prove upper bounds on the cost of our algorithm that each of these phases incur compared to the optimal solution to this problem. So let me quickly run you through an example of our first phase, which we call the hierarchical grouping phase. Okay, so imagine that lambda is 8 for now, and you have a bunch of requests to start with. Now, the hierarchical grouping phase is an iterative procedure. So it starts with every request as individual in an individual cluster. Then we keep merging clusters. So we merge two, we pair them up to form clusters of size 2. Then each of such clusters are paired and we form clusters of size 4. And finally, we have clusters of size 8, which is the maximum capacity of a vehicle. Now, it might be the case that the total number of requests is not a multiple of 8 or lambda, but that is easily taken care of by our algorithm, because only the last cluster is going to have less than lambda number of requests, which is totally fine. Okay. Now, of course, this clustering is not done arbitrarily. We cleverly design an algorithm which uses minimum cost bipartite matching as a subroutine on a very carefully designed cost function, so that the idea is that if somebody serves all the requests within a single group, then the total routing cost can be upper bounded within some factor of the optimal solution to the entire problem. Okay. Now, there is a bit of subtlety here. So our final grouping of passengers is not exactly what I showed you till the last slide. Even within a large cluster, which is shown by these sort of blue colored polygons, we may have some finer grouping. And this is like a technical requirement. We do this very carefully again in order to be able to bound the cost of our algorithm. So a brief summary of phase 1. So we do a hierarchical grouping. Each group has at most lambda many requests, as is evident. The central lemma of our paper, in fact, is that the total distance of walks inside each group can be upper bounded by square root lambda times opt. Okay, so if a taxi serves all of them within a single group, and if we now take the summation of the total distances, then that is not too large compared to opt. Okay, only a square root lambda factor. Okay, on to phase 2 now. So now the task is to do a vehicle assignment and then route the vehicles. Now, this phase, we use a slightly more standard technique, which is pretty standard in approximation algorithm, which is first computing a minimum spanning forest on a suitably defined graph. Okay, and this is pretty standard in routing literature. Because once you compute a minimum spanning tree or a minimum spanning forest, then you can convert that into a route, which is not of a very high cost. Okay. So the way we do it is we find a minimum spanning forest where the root of the trees in this forest are the initial locations of the individual taxis. And essentially, these trees, they contain the groups as some sort of super nodes, and the group now they group super nodes into individual trees. Okay, so all the super nodes inside the tree of a particular taxi has to be served by this taxi. That is the intuitive explanation of these individual trees in these forests. Okay, so once we have these trees, we can easily convert that into individual routes. That's a very standard procedure. Now, to summarize our entire algorithm, for phase 1, we lose a factor of square root lambda compared to the optimal solution, which is in the grouping phase. In phase 2, in fact, we lose this additional log n factor. We do not know of a simple way to get rid of this factor. In fact, if you remember one of my initial slides, This is also the best known approximation factor for the single vehicle case, as was given by the Fox paper back in 98. So any improvement to that would be a huge breakthrough as far as this problem is concerned. Okay, on to some experimental results. So we ran extensive experiments both on synthetic data and real world data sets. So the metrics we consider are the following. So of course, we have total travel distance, which is indeed the metric that our algorithm targets to optimize. In addition, we also compare the total in-transit latency of our routes with the baselines. So what in-transit latency really means is how much time a passenger really spends inside the taxi from the time he or she gets in to the time they hop off the taxi. Okay. So the baselines we use, both of them had been proposed in some earlier versions of VLDB. So we use FESI proposed by Zheng et al. In VLDB 2019. Well, this algorithm, the setting is very, very similar to ours, except that the objective function they consider is completely different. It's minimizing make span instead of the total travel distance. But in the paper, they showed that their algorithm works reasonably well for total travel distance. And the other one is Prune GDP, another very, very popular sort of algorithm to solve this kind of problems. And in fact, it runs extremely fast, and which is why it's even more popular, as we will see in a moment. As far as the theoretical baselines are concerned, we found that these are completely impractical, even with small data sets of, let's say, about 100 passengers. Their runtime is prohibitively large. So we do not consider them as baselines at the end. So here is a plot for the New York taxi data set. So the total travel distance plot clearly shows that our algorithm outperforms both FESI and Prune GDP, which is of course expected because we take a lot of care in optimizing this particular cost. So no surprises there. However, we were pretty surprised when we saw the total in-transit latency plot. Particularly if you look at FESI and compare it with the in-transit latency of our algorithm, in all the cases along the x-axis, our in-transit latency seems to be doing better compared to FESI, which is indeed pretty surprising because FESI had been specifically designed to handle this kind of latency of individual customers, although they do not really look at the total in-transit latency, they really look at the maximum in-transit latency. But we do not have a theoretical explanation of why our algorithm performs better than FESI, even for this objective function. Okay. On to running time now. Now, this is probably one of the major critics of our work in the current shape. Our algorithm runs slow compared to both FESI and Prune GDP, as you can see in these plots. And the primary reason being that because we want to prove approximation guarantees, we have to move away from simple-minded heuristics like greedy insertion and so on and so forth, and resort to things like mean cost perfect matching and minimum cost spanning trees. Now, although there are pretty fast heuristics to solve this problem, on large scale data sets, the runtime seems to be growing pretty high. Okay, now we have attempted to address this issue. What we did was, as you know, our algorithm is pretty modular. So we attempted to replace some of the standard modules like mean cost bipartite matching and minimum spanning forest computation with some approximate heuristics, which will not always guarantee the optimal solution, but will run extremely fast. And upon implementing them and plugging them inside our framework, we found that at least up to a data set with 10,000 taxis and about 150, 10,000 riders and about 150 vehicles, our algorithm's performance in terms of running time is not as high compared to FESI or Prune GDP as it was with the vanilla version. So I'd like to close this presentation with a couple of thoughts. So first of all, one open direction from our work should be now getting a faster algorithm which enjoys the same approximation guarantee, because we believe that giving theoretical guarantees is very important. And secondly, the question would be, right now, I'm assuming that all taxis have the same capacity. But as you know, companies might have different categories of vehicles. So, how about proving a same result for the case when the capacities of all the taxis are not the same? Our current techniques seem to be failing for such a setting. So, it should be an interesting open future direction of research. So, with that, I close my presentation. Thank you very much for your patience.